Hey everyone, today's lesson officially finishes up our section on volume here on AP Calculus A, B, and BC. This is a cylindrical shell methods, which technically speaking is not necessary for the AP test, but is probably something that you should learn. So let's get to that section right here. And it's really not much more difficult than what we've been used to. It's just your head really needs to switch gears when you start thinking of it this way. And in fact, there's a lot of integrals which are made easier by cylindrical shells. So take that for you. So there's some context here about acoustic drums, and when they're made, usually multiple layers of wood are wrapped together into a cylindrical shape. That's the first thing I thought of when I thought about cylindrical shells. In the natural world, this process is similar to an onion, where you have several layers of the onion wrapped around a central bulb. And of course, if we add all of these layers together, we get a volume. So the cylindrical shell method, it's fundamentally different in its approach to volume. It's similar because we are adding small volumes together until the exact volume is reached. But in the cylindrical shell method, we're going to basically unwrap our volume. So let's say that we're using a drum made out of a single ply, which is a layer of wood. When you unroll that single layer, what's going to be the shape of that? And provided that the layer is thin enough to unroll, we're going to get a rectangular prism, really. But let's just take a look at the rectangle. We've got a drum shell that's 5.5 inches deep and 14 inches in diameter. So if I unroll that layer, I kind of get this shape over here. And this drum shell is 5.5 inches deep. So this is going to be 5.5. And of course, this end matches up with this end over here and to create that circle. And how do I get the length of this shell? Well, the length of that shell, let's see, if the diameter is 14 inches, okay, this would actually be the radius, or I'm sorry, this circumference right here. From here to here. That's the circumference of that shell, of that one layer. So the circumference is 2 pi r, which is basically, which in our case is going to be 14 pi. So this right here is 14 pi inches. So the length of the ply corresponds with the circumference. And if the radius is x, if the radius of the layer is x inches, well then the circumference, which is the length, is going to be 2 pi r, which is 2 pi x. So what is the area of the shell? Well, in this case, this shell right here is just 5.5 multiplied by 14 pi. We don't really need a number for that. That's just how we get that. Moving on. Now we're going to actually figure this out. And if I preview here, notice we have coordinates, radius, and area formula and integration yet again. So all of this works in similar ways to the disk method and the washer method. So what do we got? The coordinates of the corners, these are already done for us, 0, 1, 2. And a little bit different here. If we have a vertical axis of rotation, then we have this in delta x, because, well, we'll get to that. But here are the coordinates, and my a is going to be x min, which is 0, and b is going to be x max, which in this case is going to be 1. Radius. Well, as is typical for the cylindrical shell method, the radius of the shell is the difference between the x coordinate and the axis of rotation. So it's always going to be x minus axis of rotation for a vertical axis of rotation. So in this case, since our axis of rotation is 0, our radius is going to be x minus 0, always x, for a vertical axis of rotation. Let's see. We know that the cross sections that we're going to look at, well, I guess the shells that we're going to wrap around, they're going to be in the shape of a rectangular prism. So the area formula is just length times width. So the length is going to be 2 pi x, because our radius is x. And then our width is going to be 2 minus x. Now, 2 minus x is how tall this is over here. I'm going to use a different color because that's kind of hard to see. This is the width right here. So it's the difference between the top, which was, 2 minus x, and the bottom, which was 0. So that gives us our area formula, and our area formula is 2 pi x. Actually, let's distribute that. That's 4 pi x minus 2 pi x squared. Okay, so when we integrate this, then we're going to just put this all together. We're going to integrate basically our area formula. And this right here is the area formula. Okay. Delta x is the thickness of the shell. Okay. Typically, 2 pi r is going to be the radius, or the width of the shell. F minus g is the height of the shell. So we get 2 pi r f minus g. So let's go ahead and integrate this. We're going from 0 to 1. So the integral from 0 to 1 of, what was this? 4 pi x minus 2 pi x squared dx. That's going to give me 2 pi x squared minus 2/3 pi x cubed from 0 to 1. And how does that finish up? That is going to finish up as 2 pi multiplied by 1, because 1 squared is 1, minus 2/3 pi times 1, because 1 cubed is 1, minus 2 pi multiplied by 0, minus 2/3 pi multiplied by 0 again, which is just 2 pi minus 2/3 pi, which is 4/3 pi. 4 pi over 3. Volume is 4 pi over 3 cubic units. So if we can get a little bit into cylindrical shell wisdom, like I said earlier, this is not technically part of the AP Calculus curriculum, or at least it's not part of the AP Calculus curriculum right now as I'm recording this. Maybe it will be back in the future again. But you're never going to get a problem that requires the use of a cylindrical shell. However, if you choose to use the cylindrical shell method, your work will be given full credit. And there are questions that are easier to do with the cylindrical shell. Cylindrical shells do not need a washer method because the hollow parts of the solids are computed when we take the height of the shell into account. And where disks and washers are kind of native, I guess, quote unquote, to the horizontal axis of rotation, the shell method seems to favor or be more native to a vertical axis of rotation. So if you have a vertical axis of rotation, you might want to think about using the shell method instead. So here's a problem. We're going to find the volume of the solid of the region in the first quadrant bound by the lines 2 minus x. 2 minus x is this diagonal line right here. Y equals x squared, which is obviously the parabola, and x equals 1. Now, I'm not quite sure why x equals 1 is necessary. I'm probably going to just go ahead and get that out. But we got the first quadrant and bound by those two curves. So that's great. Our axis, let's get the coordinates of our corners. We got 0 for our x coordinate, 1, 1, and 0. So it looks like A is going to be equal to 0. Remember, that's the minimum x. And then the maximum x coordinate here is B equals 1. Let's move on to the radius. The radius is going to always be equal to either x minus the axis of rotation or axis of rotation minus x. And in this case, the axis of rotation is to the left of the region. So at any point here, let's just draw a random shell here. This radius is going to be the x-coordinate minus the axis of rotation of 0. So the radius is going to be equal to x minus 0. Generally, you could think of this as is the axis of rotation on the left side or the right side of the region. And in this case, it's on the left side of the region. So x minus 0. Okay, so our area formula is going to be 2 pi radius times the height. So 2 pi is pretty clear. The radius is going to be x. But the height is going to be the difference between this and this right here. So up here, the y-coordinate is 2 minus x. So we got 2 minus x. And then down here, the y-coordinate is x squared. So that's our area formula. This is F, and then this is G. So F minus G. Now for the integration, we're just going to integrate the area formula. And then I think we're going from, well, A to B. So that's equal to the integral from 0 to 1. The area formula is 2 pi x, and then what is that? 2 minus x squared dx. Actually, here for the area formula, let's simplify this so we get things a little bit easier here. And I'm going to pretend I didn't write that in there yet. Let's get our area formula. That's 2 pi 2x minus x squared minus x cubed. That's everything kind of put together. And then let's put that here. 2 pi 2x minus x squared minus x cubed dx. Okay, antiderivatives here are not that big a deal. So the antiderivative of 2x is x squared minus 1/3 x cubed minus 1/4 x to the 4th power. We're going from 0 to 1. We'll do some substitution. So we got 2 pi multiplied by 1 minus 1/3 of 1 minus 1/4 of 1 minus 2 pi multiplied by 0 minus 1/3 of 0 minus 1/4 of 0. So this works out nicely in that the second substitution yields 0. So now we just got to do some arithmetic. This is 1 minus 1/3 minus 1/4, which, let's see, this is 7/12, so 5/12. 2 times 5/12 is 5/6. So this is 5 pi over 6. So we got a volume of 5 pi over 6 cubic units. Okay, here is our general cylindrical shell method. Works great for vertical axes. It's based on adding together thin rectangles, kind of like the layers of the onion or the layers of the drum. And R is going to be x minus the axis of rotation, or the axis of rotation minus x. And H is pretty much always going to be f of x minus g of x. So you can kind of count on that pretty well. And then the volume formula, remember that's based on integral from a to b of the area formula dx. A of x dx. Okay, let's move to our next bit. We've got the central body of R2-D2 can be modeled by rotating the region in the first quadrant bound by the coordinate axes, and y equals 3 minus 1/2 x squared and x equals 1 about the x-axis, where x and y are given in feet. According to this model, what is R2-D2's central volume? Okay, so for this, we don't have the coordinates of any of the corners, so let's get that. This is 0, 0 here, because we got to do 1 corners first. Up over here, this is, I don't know, let's see. If y is equal to 3 minus 1/2 x squared, then when x equals 0, y is equal to 3. So this is 0, 3. Down over here, our boundary curve is x equals 1, so that is 1, 0. And over here, that is going to be y equals 3 minus 1/2 times 1 squared, so that's 2.5. 1 and 2.5. Okay, it looks like my minimum value of x is going to be 0, and my maximum value of x is going to be equal to 1. Remember, we're rotating around a vertical axis, which means in the cylindrical shell world, everything is in terms of x. Great. Number 2, what about the radius? Okay, so in terms of this, it looks like the axis of rotation is on the left side of the region. So the radius is going to be x minus the axis of rotation, which is just equal to x. Number 3, what about the area formula? The area formula, remember we're going to be making those shells. And the area is the circumference multiplied by the height. Circumference is 2 pi r. And then the height is going to be, well, it's going to be f of x minus g of x. So 2 pi, the radius is x. The top curve is 3 minus 1/2 x. And the bottom curve is 0. Okay, so this is f up here, and this is g down here. Top curve minus bottom curve. Okay, let's simplify this. This is 2 pi. We're going to distribute that x, so that's 3x minus 1/2 x squared. And we're ready to go with part 4, which is just the volume equals the integral from a to b of the area formula dx. So the volume is equal to the integral from 0 to 1, from this right here. The area formula is this right here, 2 pi 3x minus 1/2 x squared dx. Everything looks really good. Okay, 2 pi comes out on the outside. The antiderivative of 3x is 3/2 x squared. The antiderivative of 1/2 x squared is 1/6 x cubed. And we're going to go from 0 to 1. And let's go ahead and compute that. That's 2 pi. Substitute a 1, and we get 3/2 times 1 minus 1/6 times 1 minus 2 pi. Substitute a 0, and we get 3/2 of 0 minus 1/6 of 0. And do some algebra, and this is, wait, there's a mistake. This right here should be 3 minus 1/2 x squared, making this an x cubed. That's cubed over here now. So now this antiderivative of 1/2 x cubed is 1/8 of x to the 4th power, which is 1/8 of 1 and then 1/8 of 0. And all of that comes together to 11 pi over 4. So the volume of R2-D2 central body is 11 pi over 4 cubic feet. So first of all, sorry about that miscalculation over there in that previous screen. I guess that tends to happen sometimes. Luckily, we were able to catch that. And yeah, don't be afraid of the cylindrical shell method. It really can be useful a lot of times. And we'll see you next time here for more calculus.